So for our very last section in Chapter 2, we're going to formally define what is called the derivative of a function. All right, so far when we've been taking our derivatives or finding the slope of a function, we've been doing it at singular points, right? Well, a bigger idea that we want to do is think of the derivative in terms of a function transform. And what I mean by that, the derivative is what is called an operator, which is a special type of function. So we're used to functions where I do something like if I have f of 2, you know, if you think of it like the function machine, right? You put 2 in and then whatever the output is comes out on the other side, right? So a function is just a rule that takes an input and gives us a corresponding output. Well, for most of the functions that we've dealt with up until now, we've always input numbers or even sometimes algebraic expressions and got back either numbers or algebraic expressions. Well, the derivative is a new type that we're going to call an operator, but it's really just a fancy name for a function. And the idea is we put a function in and we get a new function out. So it transforms a function into another function. So the derivative takes a function as its input and returns a new function called the derivative. So let's talk a little bit about our symbols that go along with the derivative. The symbol f with what appears to be an apostrophe after the f of x is read as f prime of x. So the apostrophe is our prime of f. So if you hear f prime, what that really means is the derivative. So f prime of x is the derivative of the function f of x with respect to x. And so according to our definition then, f prime is a new function. So we define symbolically f prime of x to be equal to the limit as h goes to 0 of f of x plus h minus f of x all divided by h. The new function that we get when we do this is called the derivative of f, or f prime. So we recognize that formula is just the difference quotient that we've been using the whole time, right? So we're just formalizing some vocabulary that goes along with our derivatives. So we need to keep talking about some symbols here. So since the derivative operator takes a function and returns a new function, there's no reason we can't just keep taking derivatives. Because if we input a function and we get out a function, we can just keep putting it back in and doing this again and again and again. So we can take what are called higher order derivatives. So we had f prime. If we want to take two derivatives of a function, we would write f with two apostrophes. So this is f double prime. Of x, and our double prime is denoted here. And similarly, we can keep going. We have three of them. That would be f triple prime. Of x. And then kind of like with polynomials, you know how we go monomial, binomial, trinomial, and then what happens after we make it to 3? We just call them all polynomials. We get lazy and we throw them all in the same basket. After we get to 3 primes, we stop writing the apostrophes because it would just make it very much too long. And we start putting a small parenthesis, and then we put a number in that parenthesis. And so this would be the nth derivative of f of x. So after 3, we stop using the prime notation, and we'll just put 4, 5, 6, 7, 142, whatever we need to put there to denote that that is the derivative that we are going to be taking. So this is the traditional Newtonian notation or the prime notation. There is another notation for derivatives called the Leibniz notation. So if we have f of x, we have our first derivative. And so we would have our f prime as our first derivative. And in our Leibniz notation, we would write derivative df dx. Continuing on this pattern, we have our second derivative. So we would have f double prime. And when we do that in Leibniz notation, we do d2f dx squared. And we continue doing this for our third derivative. We have f triple prime of x, which would be d3f dx cubed. And then, as we saw with our notation above, after 3, we just use the nth, and we would have dn f dx to the n. And each of these notations mean the same thing. So we will see both the prime notation and the Leibniz notation, the df dx, in both of them have uses. For those of you that are going to go on and study differential equations and a lot of other things, the Leibniz notation is very powerful. We will use it a lot in the next chapter when we start writing out certain rules. It is more expressive and gives more information, whereas the Newtonian notation is convenient because it's short, but it doesn't encode as much information. And we'll see that there's pros and cons depending on what you're trying to do. Sometimes you need to be very verbose in what you're trying to say, and other times being short and succinct is preferable. So we'll use both notations as the occasion rises. So we still have some more notation, but I don't want to kill you with vocabulary quite yet. So let's go ahead and do example number 1, and then we'll talk about some more definitions. So example 1 asks us to use the definition of the derivative to find f, and f prime. Well, we know what f is, because f is given, which is 5 over x. And then our definition of the derivative is, well, f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. So we plug in and we get the limit as h goes to 0 of 5 over x plus h minus 5 over x all over h. So then to simplify our fraction in this case, we multiply by the LCD of all of our denominators. So our LCD of x plus h, x, and 1 is going to be x times x plus h. So we get the limit as h goes to 0. And we're going to have x plus h, well, x times x plus h, and x times x plus h times 5 over x plus h minus x times x plus h times 5 over x, the whole thing, and then we have to multiply both the numerator and the denominator, because when I build a fraction I have to do the same thing to both the numerator and denominator of our fraction, times h. And the reason we like to multiply by the LCD on top and bottom is it always reduces out all of our compound fractions. So after this, we're left with the limit as h goes to 0 of x times 5, so 5x, minus 5 times x plus h all over xh times x plus h. So we distribute into our parentheses, giving us 5x minus 5x minus 5h all over x times h times x plus h. So then positive 5x and negative 5x add to 0. Then I have a factor of h in the top and a factor of h in the bottom. So finally, after all of this, we have f prime of x is equal to negative 5 over x plus h. And we can use our evaluation theorem to plug in h equals 0. So when we do so, we get x times x, which gives us negative 5 over x squared. So we've now found our new function, f prime. So the idea is the derivative transforms a function into a new function. So I know there's still more to do on this, but let's chat for. So if we look at a graph of f of x equals 5 over x, f prime is going to tell us about our slope of this function. So if I were to calculate, well, what is f prime of 2? Well, that's negative 5 over 2 squared, so that's negative 5 over 4. So if I go look at my graph at x equals 2, that's right here. What is this telling me? Well, what's my slope? Well, if I were to try to just draw it, I would guess it would look something like that. And it tells me my exact slope at that point is negative 5 over 4. So when I look at this picture, if I looked down in quadrant number 3, say at x equals 1, what does my graph look like it's doing down here? What's my slope going to be? Very large and negative. So let's check. What would f prime of negative 1 be? Well, it would be negative 5 over negative 1 squared, which would be negative 5. And our graph seems to follow exactly what we said. So the big key idea here is the derivative represents the slope of f. F prime of x is the slope of f of x for each x in the domain. So derivatives tell us about slope. Okay, so we're only actually halfway done. That was just a little sidebar. What else do we want to find? F double prime. Well, to find f double prime, we would take the derivative of f. So f double prime of x would be the limit as h goes to 0 of f prime of x plus h minus f prime of x, all divided by h. And f prime is what we just found above, right? So f prime is negative 5 over x squared. So this is going to be the limit as h goes to 0 of negative 5 over x plus h squared minus a negative 5 over x squared, the whole thing divided by h. So this time, our LCD for all of our fractions is going to be x plus h squared and an x squared. So x squared times x plus h squared. And we have a minus minus, so that's going to become a plus. So we build our fraction once again by multiplying the numerator and denominator by the LCD. And we get x squared times x plus h squared times negative 5 over x plus h squared plus x squared times x plus h squared times 5 over x squared, whole thing over x squared times x plus h squared times our h. So once again, as should always happen, all of our compound fractions reduce out, and we're left with negative 5 times x squared, so that's negative 5x squared, and then we have 5 times x plus h squared, so plus 5 times x plus h squared all over x squared h, x plus h squared. So now we need to expand out our numerator a little bit. So x plus h squared is x squared plus 2xh plus h squared, because it's the square of a binomial. If you just write out x plus h times x plus h in FOIL, that's indeed what you'll get. So we take that and we distribute our 5 into it. And we get negative 5x squared. So 5 times x squared is positive 5x squared. 5 times 2xh is 10 times xh, and 5 times h squared is 5h squared, all over x squared h times x plus h squared. So then our negative 5x squared and our positive 5x squared add up to 0. And we have a common factor of h in the numerator, so we factor it out, and we're left with 10x plus 5h all over x squared h times x plus h squared. So then our h's finally reduce out, and we can use the evaluation theorem. So as h goes to 0, 5h goes to 0, and h goes to 0, and we're left with 10x over x squared times x, which will reduce to 10 over x squared. So our second derivative, f double prime of x, is equal to 10 over x squared. So what is it that f double prime represents? Well, what would it tell us about? The slope of f prime, right? Because it's the derivative of f prime. We'll talk more about what the second derivative means in terms of f at a later date. But for right now, we've found another derivative. So to find our derivative, we have that f prime of x is equal to the limit as h goes to 0 of f of x plus h. So in this case, it's going to be x plus h squared plus 5 times x plus h minus f of x, which is x squared plus 5x, all divided by h. So then we need to multiply all of this out. So x plus h squared is x squared plus 2xh plus h squared. Distributing the 5 in, we get 5x plus 5h. Distributing our minus sign in, we get x squared minus 5x, all divided by h. So then we have a positive x squared and a negative x squared. We have a positive 5x and a negative 5x. So now all of the terms that are left all contain a common factor of h. So factoring out our h leaves us with the limit as h goes to 0 of 2x plus h plus 5, all divided by h. And then our h's reduce out. So finally we can evaluate our limit, and as h goes to 0, that h goes to 0, and we are left with 2x plus 5. So the derivative of x squared plus 5x is 2x plus 5. So we talked about how before the derivative of f is the slope, or f prime is the slope of f. If we think back to 2.7, for example number 1, it says a particle starts moving to the right along a horizontal line. The graph of its position function is shown. Use the graph to answer the following questions. Well, what did we decide the velocity of the position function was? Well, when we graphed our velocity function, what did we graph? We graphed its slope, right? So in terms of physics and reality, what does the derivative represent? It represents a rate of change. So if your function f represents position, what would its derivative represent? Velocity or speed. So in terms of physics, if we have f of x represents our position function, then f prime of x represents the velocity function. F double prime would be the rate of change of velocity. So what do we call the rate of change of velocity? So how fast your velocity is changing is called acceleration. And then lastly, f triple prime, or the third derivative, is what's called jerk, which is the rate of change of acceleration, right? So in terms of physics, we have position, velocity, acceleration, and jerk. So turns out calculus is very, very useful in many, many branches of science, including physics. So does anybody happen to remember what Newton's second law is? Newton's second law says mass is equal, or force is equal to mass times acceleration, right? So F equals ma, but a is the second derivative. So in terms of physics, force is equal to mass times the second derivative of position. So d2s dt squared. This gives rise to what is called a differential equation. We'll talk about those later, but if you've ever wondered how scientists know when that asteroid's going to come screaming by Earth, well, it's because we're going to solve these types of things backwards. If you can observe an object's acceleration and you know its mass, you can then solve backwards to recover its velocity and position functions, right? That's our big goal by the end of Calculus 1. So that's like our foreshadowing of the end. That's Chapter 5. We'll start doing that process. But the idea is if we start with position, we can differentiate all the way down to acceleration and jerk. At some point, every time we learn to do something in math, what do we have to learn how to do? How to undo it, right? We learn how to add, then we learn how to subtract. We learn to multiply, then we learn to divide. We learn about exponentials, and then we learn about logarithms, because we have to be able to reverse everything we want to do. So it's kind of the big picture of where we're going to go for the next couple of chapters is building up the idea of derivatives and then how we are going to undo derivatives. All right, so let's take a look at our next example. So we want to find the derivative of this. Luckily, the Hint Ninja has shown up to give us a hint. So we want to use the definition of the derivative to find the derivative of x to the fifth minus 3x. And it says use the binomial theorem that a plus b to the n is equal to the sum as I goes from 0 to n of n times, or n choose I, a to the I, b to the n, I. Well, let's work this out separately for each of these, because we know we're going to need to calculate f of x plus h at some point. Well, f of x plus h is x plus h to the fifth minus 3 times x plus h. Well, this guy, we just distribute the negative 3 in and we're good to go. how are we going to calculate x plus h to the fifth? Well, the long way would be to write out x plus h times x plus h times x plus h times x plus h times x plus h and multiply out those 5 binomials, right? Well, this is where the hint ninja says, well, wait a minute, x plus h to the n, or x plus h to the fifth, is equal to this sum as I goes from 0 to 5 of 5 choose I, a to the I, and our a in this case is going to be x, and our b is going to be h. So we're going to have our a raised to the I and our b raised to the n minus I. Let's replace each of these with what they are. So we have x and we have h. So we may or may not know what this symbol is. This is called the choose symbol. And the choose symbol has the following formula. So if we have n choose k, it is equal to n factorial divided by k factorial divided by, or times k factorial times n minus k factorial. And the factorial function, the exclamation point after a variable, doesn't tell us to scream n. It tells us to multiply all of the numbers, the whole numbers, starting at n all the way down to 1. So for example, 5 factorial would be 5 times 4 times 3 times 2 times 1. So 5 times 4 is 20, times 3 is 60, times 2 is 120, times 1 is 120. So 5 factorial is equal to 120. The good news is our calculator can actually calculate these for us. So let's talk about where we can find these symbols on our calculator. So if we press our math key and we move all the way over to PRB under math, which stands for probability, our calculator uses a slightly different notation, which is going to be choice number 3. So on our calculator, instead of doing n choose k, we're going to do n, and then it's going to be c, and they use r instead of k. But it doesn't really matter, because those are just placeholders for numbers. And this is under math, and then we go all the way over to probability. So let's go ahead and calculate, say, 5 choose 3. So 5 choose 3, you have to put the 5 in first. So you go 5, math, all the way over to probability, choice number 3, and then 3. And it tells us that 5 choose 3 is 10. And we could keep doing that. So if I wanted 5 choose, say, 2, put that in, it's also 10. If I want 5 choose 4, that gives me 5, and so forth. So now back to what we are actually trying to calculate, which is this piece right here. So writing all of this out, we have our sum as I goes from 0 to 5. We're going to get this is equal to 5 choose 0. X to the 0 is 1. And in this, our n was 5. So we get 5 minus 0, so we get h to the 5th, plus, when I equals 1, we get 5 choose 1, x, h to the 4th, plus 5 choose 2, x squared, h cubed, plus 5 choose 3, x cubed, h squared, plus 5 choose 4, x to the 4th, h, plus 5 choose 5, x to the 5th. So we'll notice what happened when you formally write this out. One of the variables starts with an exponent of 5 and counts down to 0. The other variable starts with an exponent of 0 and counts up to 5, right? And our choosing is always whatever our exponent was, which is 5, and it also counts up from 0 to 5. So if we punch those into our calculator, 5 choose 0 is 1, so we get h cubed. 5 choose 1 is 5x h to the 4th. 5 choose 2, as we did on our calculator, is 10. So plus 10 x squared h cubed. 5 choose 3 is going to be 10 x cubed h squared, plus 5 choose 4 is back to 5, so we get 5x to the 4th h, and 5 choose 5 is 1, and we get x to the 5th. So let's add some highlighter to help us out. So that's going to be the coefficient, which is a 1. 5 choose 1 is 5. 5 choose 2 was 10. 5 choose 3 was also 10. 5 choose 4 is 5. And lastly, 5 choose 5 is the coefficient of 1. And then our variables come down for the ride. So that would be x plus 5, or x plus h to the 5th power, right? If we expanded it all out, we get h cubed plus 5xh to the 4th plus 10x squared h plus 10x cubed h squared plus 5x to the 4th h plus x to the 5th. So all of that work was to get just what piece? Just this, right? And what's our formula? F of x plus h minus f of x all over h. So this part is almost f of x plus h. So let's finally take our derivative. So f prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h, which is the limit as h goes to 0 of our h to the, that should be a 5. That looked a little bit like a 3. H to the 5th plus 5x h to the 4th plus 10x squared h cubed plus 10x cubed h squared plus 5x to the 4th h plus x to the 5th. But then don't forget, we also had this negative 3 times x plus h, which is negative 3x minus 3h minus f of x, which is x to the 5th plus 3x, all divided by h. So then, what happens? Same thing that happened in all of our examples. The x to the 5th and the x to the 5th cancel out. There is a negative 3x and a positive 3x. When we look at what's left in this, every single term will then have an h, which we can factor out. So we factor out our h. And we have h to the fourth plus 5xh cubed plus 10x squared h squared plus 10x cubed h plus 5x to the fourth and then, oh, there it is. I'm like, there should be one more thing, minus 3 all over h. And our h's reduce out, so we finally take the limit as h goes to 0. So that goes to 0. That has an h, so it goes to 0, goes to 0, goes to 0. And what are the only two things that are left? 5x to the fourth minus 3. So that is f prime. Woo. All right, so we're going to switch to a more geometric interpretation of what we've been doing. So example 3 says, use the graph to identify f, f prime, and f double prime. So what did we say the key idea is? What is it that f prime represents? The slope of f. And f double prime would represent what? The slope of f prime, right? So our goal is we have 3 graphs, and we want to determine which one's f, which one's f prime, and which one's f double prime. So the way I like to do these, and everybody has a different thought on the matter, is I just pick one and start analyzing and see what we have. So I don't really care which one we pick. So what's our favorite color today? Red, blue, or green? Green. Okay, so let's start with the green graph and start analyzing. So when I look at the green graph, it's down here. What is the slope of the green graph always? So as we move from left to right, what does the green graph do? It's always going up. So what does that mean about its slope? Perfect. So the slope of the green graph is always greater than 0. And what else do we know about it? What does its slope get close to? Well, when it starts out, the graph is really, really steep. So what does that mean about the slope? Is the slope big, or is the slope small if the graph is really steep? It's big. And as I move from left to right, what happens to my graph? It flattens out. So what does its slope get closer and closer to? 0. So the slope starts big and goes to 0, right? So it starts as a big number and goes to 0. Do we have a graph whose y values do that? Because remember, the derivative represents the slope. But when we're talking about the derivative, the output is the y values. So when we were finding our slope back here, right? To find our slope at 2, we put the x value of 2 into our graph right here, and that told us what the slope of the graph was, right? So the outputs of the derivative are the slope. Well, outputs live on the y-axis. So do we have a graph whose y-values are always bigger than 0 and whose y-values start really, really big and get close to 0? Yeah, which graph is that? The red graph, right? Because its y-values start way up here, and its y-values decrease, 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 and they decrease, and then it starts flattening out, and its y-values getting closer and closer and closer to the number 0. So our red graph looks like it should be the derivative of green, right? So it appears, so the red graph, the y-values, fit this above, right? Its y-values are always positive, they start big, and they get close to 0. So then this would imply red is the derivative of green. Right? We don't know who is who, but now we know red is the derivative of green. So we've already analyzed green, and we've made a chain with red. So red seems like the next logical thing to look at. So when we look at our red graph, what observation can we make about its slope?
Decreasing.
Yeah, the slope is always decreasing, right? Because it moves down as we go from left to right. So the slope of red is always less than 0, and its slope is going to be a large negative number. So and it's going to go to 0 from that side. So now the only one that's left is blue. Do the y-values of blue fit that pattern? Well, what are my y-values of blue? Well, they're always positive. Oh, so that's a problem, right? So if the y-values of blue are always positive, and do the y-values of blue get close to 0? No. So is blue the derivative of red? No. So we know blue's not the derivative of red, so the only thing that we have left to check then is, since we know red is the derivative of green, by the process of elimination, green better be the derivative of blue, but let's verify that that's the case, right? So if we look at blue, what do we have? What's our slope for blue? We have blue always has a positive slope. And what do we know about its slope? What always happens with our slope? It's always positive. And is our slope increasing or decreasing? Well, when we look right here, the graph is going up. It's really steep. And the further we go out, what's happening to each of the tangent lines? Does my slope get bigger, or does my slope get smaller? Is it getting steeper or flatter? Flatter. So my slope is going to start big, and it's going to decrease to 0. Okay. So our slope starts positive, and it decreases to 0. Oh, wait a minute. notice what we have here. So the green and blue have the same profile, right? So what does that tell us? Green had a positive slope and its slope started big and went to 0. Similarly, so does blue. So maybe then we had our initial guess wrong, right? Because they both fit. So we guessed that red was the derivative of green. But what could red also be? Red could also be the derivative of blue. So this one says that red could also be the derivative of blue. And only one of these can be right. So we found out that we had a bit of a problem with the bottom one. So if red is the derivative of blue, what about the slope of red? Well, let's analyze the slope of red. So the red slope we already did the red slope. So we've done green, red. I think we've done all of them. So now let's see if we can figure out what our chain is. So red is the derivative of blue. And if red has negative slope and its slope goes to 0, do we have a graph that fits that? Well, what are the y values of green? Are the y values of green positive or negative? Negative. And what do they get close to? 0. Does that fit our red graph? Sure. Its slope is always negative, so the y values of green tell us about the slope. So green is always negative, so our slope is always less than 0. And do our y values of green get close to 0? Indeed they do. So if red is the derivative of blue, we can then also conclude that green is the derivative of red. So then that would make blue is F. And red is F prime. And then green is the derivative of red, so that would be F double prime is green. So when we have multiple graphs to compare, we have to start off by just picking one. As we did it this time, did we pick the right one the first time? We made a valid analysis, but then when we tried to make our chain, it didn't work. So what did we do? We tried a different pairing and checked to see if that worked. And that one led to the correct conclusion. Key idea, the derivatives y values tell us the slope of the original graph, right? So it's really easy to get kind of tripped up because at one point you're thinking about slopes and on the other one you're thinking about the y values. So you've got to keep those two things straight. Y values versus slopes when we're doing this analysis. The y values of the derivative are the slope of the function it's a derivative of. So just be a little careful. It takes a little practice to get that all sorted out in your mental picture. All right. All right, so for our next example, we want to talk about, well, where is this function not differentiable? So what was it that the derivative represented again? It's the slope. So what we would have to start looking for is places where the graph does not have a well-defined slope. Well, by glancing at this picture, there's a couple of places that should really jump out at you, pun intended, right? Anywhere our graph has a jump discontinuity, can we talk about the slope there? No, because the graph is broken into multiple parts. So it turns out that the graph is not going to be differentiable anywhere it's not continuous. So to be differentiable, so one thing to note about that is that this is what is called a necessary condition, but not sufficient. So what that means in logic is that the graph has to be continuous. If it's not, it can't be differentiable. But being continuous by itself is not enough to guarantee differentiability. So it's necessary, but not sufficient. So we know if it's not continuous, then indeed it's not differentiable. But to be differentiable, we need a little bit more. The slope has to be the same on both sides of whatever point you're talking about. So the informal way to talk about this is the graph must be smooth. And for right now, we're going to leave smooth as an undefined term. So we're going to have it mean what you think it means. It can't be sharp and it can't have any corners. It has to be nice and smooth. What it formally means is that at every point, the limit of the slope on the left is equal to the limit of the slope on the right. That's the more technical meaning of what we have. So the point of interest that we want to look at right here is at x equals -5. So if I were to look at that point right there, well, to the left of -5, so -6, -7, well, what's my slope going to be? Well, I can just calculate my slope, right? Because it's a line. So if I wanted to, I could calculate the slope of this by just going rise over run, right? 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, 6, 7, 8, 9. But it's negative. So my slope right here, or my derivative, whichever way you want to put it, would be -9/5, right? Well, if I look on this circular arc right here, what does our slope look like right here at this point? Is my slope going to be smooth? No, it looks like my graph goes almost straight down at that point. In fact, it does, it turns out. And then what happens? My slope changes and starts flattening out till I get to a slope of 0 over here. So here, this slope, right at that point, does not equal -9/5. So this is not smooth. We don't really need to do quite that in-depth of an analysis. So we're going to refer to any sharp corner is called a cusp. So that is an example of a cusp. Functions are not differentiable at cusps. Or jumps. Or, for that matter, at any discontinuity. A graph is not differentiable at any cusp or anywhere where it's discontinuous. So we needed to figure out where this graph is not differentiable. So it's not differentiable at x equals -5, or x is equal to 1, or x is equal to 4. And that would be all of our places where our function is not differentiable.